Good morning and good afternoon, everyone. On behalf of the organization committee of the special session on fractal interpolation and iterated function systems, I, Megha Pandey, would like to extend my warm welcome for the last installment of this 2 days special session. So, after successfully completing the first day, let's move forward to the last installment. And the first speaker of this session, of this part, is Professor Takayuki Watanabe from Chubu University, Japan. The title of his talk is On the Topology of the Limit Sets of Non-Autonomous IFS. So let's welcome him and over to you, Professor.
Thank you very much for your introduction. And I am Takayuki Watanabe from Chubu University. First of all, I'd like to thank the organizers, in particular for Murinar, for giving me this opportunity. Today, I'd like to talk about the topology of a kind of fractals. This is joint work with Yuto Nakajima from Doshita University, Japan. And you can see a new preprint on archive, so I hope you can enjoy it. And our essential idea is summarized in these figures. On the one hand, we have a fractal. And as you know, fractal has a very good features, a self-similarity. From these self-similarities, we can extract the information of intersections. And by using these intersection structures, we can calculate its combinatorial structures. In particular, we can calculate its homology groups or cohomology groups. Okay, so let me start my talk. First, I'd like to define what the non-autonomous IFS is. And later, we will discuss about simplicial complex for non-autonomous IFS. By using them, we deduce Hatter's type theorem and homological result for them. So let me first define non-autonomous IFS. Here, our phase space is a compact metric space, X, and in usual IFS theory, we fix finitely many maps, but in non-autonomous setting, we have a sequence of maps. That is, we have a phi superscript j, which consists of a finitely many maps, f subscript I, superscript j. Here, the subscript I moves finitely many indices. And for these maps, we denote the Lipschitz constant by lip of f. And we assume that there is a uniform constant C such that Lipschitz constant of every map is at most C for every time j and every index I. We call such a sequence of collections of maps a non-autonomous iterated function systems. And for this non-autonomous IFS, we define the limit set as follows. We iterate fi, f2, blah, 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 fj, and consider its unions, where i's subscript runs over all indices, and taking its intersections, where j runs over 1 to infinity. So this is a very natural generalization of usual IFS theory. More precisely, if this phi j is identical, phi, 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 then this is usual autonomous IFS. And the limit set coincide with our settings. So let me first introduce some previous studies. Hatta considers the connectedness of limit set for autonomous case. For autonomous iterated function systems, we consider the limit set J. Then the following are equivalent. The limit set is connected, J is path connected, and we have intersections in a chain-like manner. So let me go more precise. We first fix indices I and I prime, say in Sierpinski carpet figures, I and I prime is like this. For fixed indices, there is finitely many indices I naught, I1, blah, 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 In, starting from I and ending at I prime. they satisfy that each consecutive small pieces intersect each other. So if this kind of thing happens, then the limit set is connected and path connected at the same time. So by using Hata's theorem, the Sierpinski carpet is connected. We can deduce it. And the middle one is also connected. But if we consider this kind of fractal, this is not connected. This fractal is made from 3 by 3 smaller squares by removing 1, 2, and 3 pieces here. In this case, the right lower one is isolated. It does not intersect another miniatures, so that this fractal is not connected. Moreover, for some special kind of fractals called fractal square, we have some topological result. Let me first define it. Now our phase space is a unit square. And for this X, we divide it into n times n smaller rectangles. And for each square, we have a contractive map from larger unit square to this smaller squares. So we have n squared small contractive maps. And for each j, if we fix some non-empty subset ij, then this form a non-autonomous IFS. So for this class, some previous studies exist. For example, Lowenstadt gave an equivalent condition for autonomous limit set to be totally disconnected. So by combining Hata's result, we can decide which fractal is connected or which is totally disconnected. Later, Shao gave an equivalent condition for autonomous J to have finite remaining connected component. These two are for autonomous fractals. But Christer studies randomly generated non-autonomous fractal squares. She studies the connectedness and total disconnectedness of this kind of randomly generated fractals. So in this talk, we want to generalize their result toward non-autonomous limit set and more. Okay, so here is what we shall do. So we want to consider topology of fractal. This is not fully understood, I think. But as you know, the dimension theory is well developed so that we can calculate its Hausdorff dimension of fractal square or some more. And we shall generalize Hata's theorem on connectedness to the non-autonomous setting. And moreover, we want to investigate the homology group of these kind of fractal squares. That is our motivation. So here, I want to introduce my main tool. Before that, we introduced the Hutchinson type formula, which exhibits self-similarities. Let phi k be a non-autonomous IFS, and for every j, we consider non-autonomous IFS starting from phi j. Next one is j plus 1, blah, blah, blah. So we forget j minus 1 first term. For this new non-autonomous IFS, we denote its limit set by j sub j. Obviously, j1 is equivalent to the original limit set j. And for this sequence of limit set, if j and k satisfies this inequality, then jj can be written by the copies of jk. So this figure says that j1, this is consists of small copies of j2. j2 is here. And j2 consists of 3 copies of j3. j3 is here. So consequently, j1 consists of 9 copies of j3. In this sense, we have a self-similarity in a broader sense. And by making use of these structures, we want to calculate some topological structures by using the nerve. So for J and K, we define the simplicial complex NJK as the nerve of its covering. So if you want to consider N1, 2, then you need to take care of J1 consists of small copies of J2. In this case, we have 3 copies of J2, and each represent a vertex of simplicial complex. Nerve says that if these 2 copies intersect, then we put a simplex of dimension 1 here. Since these 2 intersect, we put a 1 simplex here, but right upper one and left lower one does not intersect, so we do not put a 1 simplex here. If these 3 have intersection, then we put a simplex of dimension 2 here, but now we do not have it, so we do not put a 2 simplex here. This is a definition of N12. N13 is the case where we consider small copies of J3, and again we do the same thing. Blah, 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 blah. So we have a sequence of simplicial complex. And actually, this is enough to have a homology groups. We define a simplicial map from jk plus 1 to jk by forgetting the last word. Actually, we can check that this is simplicial so that which induce group homomorphism on homology groups. So we have a sequence of homology groups and its homomorphism. And this form so-called inverse system. And we can take limit, that inverse limit, as k goes to infinity. And our theorem says that there is an isomorphism from the inverse limit of these homology groups to the check homology group. Here, the check homology group is the inverse limit of nerve of finite open covering of U. And dually, there is an isomorphism from direct limit of cohomology groups to check cohomology group. So in a simple way, we can calculate check homology and check homology group. By making use of it, we can consider Hatter's type theorem. So for connectedness, we have the following. On the one hand, we have a component of simplicial complex. This is purely defined in terms of combinatorial structures. For topological space, we also have a connected component of topological space, and we write P con of Y for the set of all path connected components. Our theorem says that these are bijective. More precisely, for a connected component of topological space J, we can define a simplicial complex CK by these inclusions. On the left-hand side, this is a subset of J itself. And as I said, J consists of these kind of copies coming from JK. So that by considering its subset, we have this kind of inclusions. And actually, this map satisfies some commutative diagonal structures so that it induces a map towards the inverse limit of con of N1K. And actually, our theorem says that this is bijection. Moreover, from path component to the same one, we have a bijection in a very similar way. So by making use of it, we can deduce a Hatter type theorem. We say that the following are equivalent. The limit set is connected, the limit set is path connected, and for every k, n1k is connected. And actually, this third condition is equivalent to say that we have a intersection in a chain-like manner. This is very similar to the original Hatter's theorem. And not only connectedness, we have more. For local connectedness, we have a sufficient condition. If n sub k plus 1 is connected for every k, then the limit set is not only connected, but also locally connected. This is a generalization of the case where the limit set is autonomous. But remark that if autonomous limit set is connected, then it is locally connected. However, this does not hold for non-autonomous limit set. That is, for non-autonomous settings, even if the limit set is connected, it cannot be locally connected. So this makes a difference between autonomous and non-autonomous limit set. And for total disconnectedness, we have the following. As I said, we have an inclusion here. And by taking its diameter, we can have some estimate for the connected components. Since our maps are uniformly contractive by a factor c, we can say that if this right-hand side converges to 0 as k goes to infinity, then the diameter of connected component is 0. So if c to the k times maximum of number of vertices goes to 0 as k goes to infinity, then the limit set is totally disconnected. So by seeing its combinatorial structure, we can say something about connectedness, local connectedness, and total disconnectedness. This can be regarded as H0, zeroth homology groups. So we want to consider higher homology groups. We want to consider fractal rectangles in these sections. Here is a definition of non-autonomous fractal rectangle. Again, our phase space is unit square. And here, we divide it into n1 times n2 smaller rectangles. And for every rectangle, we have an affine contractive map, Fi. There is n1 times n2 indices. But we randomly choose it in the following sense. Fix some number r, then we randomly choose each ij independently so that its complement has precisely r element. Or in other words, we remove r element at each time, but we do it randomly, independently. So with a uniform distribution, we form an autonomous IFS and randomly generated fractals. And our theorem says that if the number of removable r is smaller than 2, then check H0 of J is isomorphic to Z, which means that limit set has only one component, so J is connected. And actually, in this case, J is locally connected as well. So the left figure is the case where 3 times 3 squares, and we remove one piece at each time. In this case, this is connected. But if we remove 2 or more pieces, then it can be disconnected. For example, on the right upper corner, you can see an isolated component. So if we remove 2 or more, then the limit set is no more connected. Moreover, if R is 2 or more, then the connected component can be infinitely many, almost surely, with probability 1. Also, for total disconnectedness, we define a cut here. Let I prime be a subset of indices. We say that this has a horizontal cut if there exists some index I such that its projection onto second coordinate does not include the element I. So you can see a cut here. Similarly, a vertical cut is defined by considering its projection onto first coordinate. If the indices has horizontal cut infinitely many times and vertical cut infinitely many times, then the limit set is totally disconnected. Moreover, we can calculate the homology groups as well. For every Q, 2 or more, then check homology group of Qs vanishes. This is due to planar fractals. This is because we are working on fractals on R2. So our main interest is first homology, H1. If number of removable is 1, then as I said, the limit set has only one connected component. But if we consider 2 by 2 fractals, then check H1 vanishes. If not, then first homology grows exponentially fast. And actually, its growth rate coincides with topological entropy for this case. If R is 2 or more, but it is smaller than N1 and N2, then in this case, we have exponential growth. And again, its growth rate is coincide with entropy. In this case, rank of H0 is also infinite. And of course, rank of H1 is infinite. If R is N1 or more, but smaller than N2, in this case, we have infinitely many horizontal cut. Consequently, check of H1 vanish. But in this case, we have infinitely many connected components. But in this case, J contains a line segment, so that J cannot be totally disconnected. But if we remove sufficiently large numbers, then the limit set is totally disconnected. This kind of thing happens with probability 1. Let me show you some figures. In this example, we consider 3 times 4 rectangles. And at each time, we remove R rectangles. Here, R is 1, 2, 3, and 4. If we remove only one piece, then it is connected, but we have infinitely many holes, say here, say here. This is the case where R is equal to 1. If R is equal to 2, then we can have disconnected fractal. Actually, there is infinitely many connected components. But at the same time, there is infinitely many holes on the fractal. And if R is equal to 3, then there is infinitely many connected components, but H1 vanishes. There is no hole, since it is cut horizontally infinitely many times. But in this case, the limit set contains a line segment, say here or here. Consequently, J is not totally disconnected. But if R is 4 or more, then the limit set is totally disconnected. So we can luckily calculate its homology groups. And actually, this homology group is free abelian group. So consequently, we can calculate cohomology group at the same time. This is isomorphic to the free abelian group of the same rank. So these two are isomorphic. By the Alexander duality theorem, if one knows the check cohomology groups, then we can deduce an information about connected components of its complement. More precisely, let D is to be 2 and Q to be 0. Then first check cohomology is isomorphic to the reduced homology of zeroth homologies. So we can calculate the number of bounded connected component of complement of J. So this number is 0 over infinite, depending on its first check cohomologies. Okay, so here is a summary of my talk. I stop here. Thank you very much.
Thank you so much, Professor, for the talk. So now I would like to request to the audience if they have any question for the speaker. Okay, so if not, let us thank the speaker for such a nice presentation. So, since the next talk after this is the next talk is cancelled, so we will take a break of 30 minutes and then we'll meet in 20 minutes after this. Okay, for our next talk.
Hello,